Hi, this is Math 2520, and this video is going to be over section 6.7, which will look at some physical applications, or physics for that matter, using integrals. One of the common integrals deals with work. This one particularly will be with a constant force. When we say something is work, usually we mean the total amount of effort we need to put forth to complete a task. In physics, though, it's a little bit more technical. It has to do with a force and its push and pull on an object, and how much of that is happening over time. Right, so force is mass times acceleration. Or if you're dealing with gravity and you're looking at like weight, it could be where A equals G and your force is mass times gravity. And we usually call that the weight of an object. And where gravity itself is 9.8 meters per second squared. If we have constant mass and acceleration, then the force is also constant, and the work done is going to be the force times your change in distance. So how far that force is applied. And so we'll have force times x2 minus x1. Right, again, force is m times a. Couple other things to know we're getting into this is density is mass over volume, and mass itself can be written as density times volume. And then certain things, again, as we get into this, mass is measured in kilograms, displacement in meters, or distance in meters, time is seconds, force is newtons, and work is going to be measured in joules. Okay, so 1 joule equals 1 newton meter, so force times distance. Right, so how much work does Harriet do when she lifts a 20 kilogram dumbbell a height of 3 meters? Well, the work is your force times x2 minus x1, and so it would be the force, you're lifting a dumbbell, so it's a mass times gravity, you're going against gravity there, and then the distance is 3 minus 0, so she lifts a height of 3, so she goes 3 meters basically, so 3 minus 0. And so we have 20 times 9.8 times 3. And this is about 588 joules. Okay. How much work does Barry do when he lifts a 30-pound weight 7 feet off the ground? Right, certain things changed. Force is no longer 20 kilograms, but it's 30 pounds. Pounds itself is a unit of force, so 30. And then you're going 7 feet off the ground, so 7 feet is your change in x. So 210 foot-pounds. Okay. So it's not joules, but it's in foot-pounds. So we can convert it to joules if we have the conversion, but otherwise we won't keep it at foot-pounds. Alright, so work is very easy when the force is constant. Okay, so what happens when it's not constant? So suppose I have an object moving along x-axis and I have a varying force. I can write this as f of x, where that's the force. And then I am summing up this force. So my change in work is going to be all the little xi's of the forces summed up times my change in x, whatever that distance is. And I can rewrite this as a limit as n goes to infinity, infinite number of individual sections here, times the summation from I going 1 to infinity. Well, I probably should have kept that as I to infinity, but f of xi times delta x. Okay, and this would then become integration from a to b of f of x delta x. So that's how we go from varying force to having an integral there, or you're adding up all the little individual spots depending on how the force varied. And so the work is then integral from a to b of f of x dx. So suppose an object is located distance x feet from an origin, has a force that's x cubed plus 1 acting on it. How much work is done in moving it from 1 to 2? So our f of x is x cubed plus 1. So work is integral from 1 to 2, x cubed plus 1 dx. This is going to be x to the 4th over 4 plus x, integrated from 1 to 2. We don't put the plus c's because we have limits. And so we'll have 2 to the 4th over 4 plus 2 minus 1 to the 4th, which is 1 over 4 plus 1. Alright, so 2 to the 4th is 16 over 4 is 4, so we'll get 6 here minus 3/4. Oh, I'm sorry. 6 minus, I had subtracted that because of the subtraction sign. 6 minus about 1.25, 5/4. So we'll get 4.75. Now our force was in feet, is our x. So our force will have to be in pounds. I know it doesn't say it, but we'll have foot pounds or pound foot. Yeah, if we look at Hooke's law, it's the force required to maintain a spring stretch x units beyond its natural length. Right, so again, if this is some wall, and then we let it save to some wall, you have a spring on it. That's the natural length. And then that same wall, the spring is stretched by some force. Okay. That force f of x is going to be equal to kx, spring constant times how far it gets stretched. Okay. So a spring has a natural length of 20 centimeters. If a 25 Newton force is required to keep it stretched to a length of 30 centimeters, how much work is required to stretch it from 20 to 24? Right, so f of x equals kx. Right, and so what we're going to do is first find k. So k is your f of x over x, and we use 25 newtons to keep it stretched of 30, keep it stretched a length of 30 centimeters. So we're stretching it 10 centimeters. So 0.01, which ends up being 250. Right, so we can write our f of x as 250x. And we want to find the work. to go from 0 to 4 centimeters. 20 to 24 is the same thing as 4 centimeter stretch, so 0 to 4 makes the math easier by using lower limits here. We'll have 250x dx. So when we integrate this, we get 250 over 2 x squared from 0 to 0.04. It's going to be 125 0.04 squared, which is 0.2. This will be joules, since I'm dealing with meters and newtons. Since this was 25 newtons over meters. Alright, so let's do one where we have to find the force function. So a 800-pound box of baby chinchillas is at the bottom of a 500-foot pit. Luckily, we have a rope that weighs 2 pounds per feet that goes from the top of the box to where we are. How much work will you have to do to save these baby chinchillas? So, draw a little picture here. Box, the rope, and this is 2 pounds per foot. This is from 500 to 0. We can think of it as 0 to 500. That's how far it has to go. And this is also 800 pounds force downwards. So the force here would be 800 pounds plus 2 pounds per foot. That's 500 feet. So we're looking at 1,800 pounds force. And then also looking at, and we can think of it as force 1, 800 times 2 pounds per feet at the 0 point, and we'll look at 800 pounds. Okay, so our force is varying from 800 to 1,800. Okay, so we can write an expression for this as 800 plus 2x, where x goes from 0 to 500. And so we have an integral from 0 to 500 of 800 plus 2x dx. So we'll have 800x plus x squared going from 0 to 500. So there's 800 times 500 plus 500 squared. And so this will come out to be 650,000. Okay, and this will be, we're looking at work, so this will be foot-pounds. Alright, another type of application is hydrostatic force. Okay, remember that with like gravity, F equals mg, density is mass per volume, mass itself is density times volume. Never know when these come up. Volume is going to be area times distance. Okay, this definitely comes up when you're dealing with liquids and pressure. When we swim in the water above us has a force on us. So we feel pressure, and we define this as that force over a certain area, which is mass over gravity over that area, which is density times volume times gravity over that area, which is density times area times distance times gravity over that area, but the areas cancel out, so you get density times distance times gravity, or distance being depth. So for pressure, for when you're underwater, pressure is not pressure, but density, gravity, and depth. Units for pressure, either newtons per meter squared, or that's also called a Pascal. A lot of times we use kilopascals, especially when we're dealing with chemistry. Density for water is 1,000 kilograms per meter cubed, or 62.5 pounds per foot cubed. And then the pressure at any point in the liquid is the same in all direction. And then pressure in any direction at depth D in the fluid is given by what we just found, the density, gravity, and depth. The pressure varies with depth, and we have to set up an integral resulting from taking the limit of the force at each depth. Right, so a tank is 4 meters wide, 5 meters long, 3 meters high, and contains the liquid with density 800 kilograms per meter cubed, so a little less than water, to a depth of 2 meters. Okay, if we want to find the hydrostatic force in the bottom of the tank, F equals the pressure times the area, since pressure is force over area. We're just multiplying the area over, which is going to be the density times gravity times depth times the area, which is going to be, since it's a container, length times width. Length being 5, width being 4. And so we'll get 800 times 9.8, that's your gravity, times 2 for your depth, times 5 times 4. And this comes out to be 313,600 newtons. And now what we're going to do is set up an integral to find the force on one end of the tank. Let me draw it better. Okay. So this is the water level. Okay. And so your x is going to be down. And so, you know, how far you go down, that's your delta x. Okay, so delta area is the width times delta x of this strip. So width being basically find a little section there, a little rectangular section of this tank. And then the delta force is pressure bearing with x times the delta area. Pressure being the density times gravity times the depth times the delta area, which is going to be density times gravity times our x times w dx. And so when we integrate this, we'll get force integral density times gravity. I don't like density looking like a P. Times the width x dx. And it's going to go from, what does it say, from C to D, since it's vertical. Or 0 to D. 0 to the depth. Alright, so when we integrate this, we're integrating with respect to x. So we'll have the density times gravity times width times x squared, going from 0 to the depth. Over 2. Forget to divide by 2. And so when we plug in the depth, we'll get density, gravity, width, depth squared over 2. Alright, so here we want a separate integral that expresses the hydrostatic force against one side of a vertical plate that is submerged in water, with the shape indicated by the picture below. So this is 1 foot below the surface of the water. And so our dA is going to be our width times x dx. Oh, I'm sorry. Width function, not width times. It's going to be w of x dx. That's why there was 2 x's there. Now we have to find what our wx is. And we can look at this through kind of how this distance is, how it's changing. So it starts out at 4. And as you go over 3, let me hold on, let me define something first. Make sure that is understandable. So our width, our wx, is this part here. Oops, trying to check. This part here. And notice that is changing as you go up. That's going to be different than up here. Okay, it's a different size. And then this is going to be our dx. Okay, so it's a different size. So like in this problem, it was rectangle, so the width stayed 4. Here, the width is changing. Okay, so that's what I'm going to do over here. Is at the very top, from here to here, it's 4. Then it goes down to 0. And it goes down to 0 when you drop down to 3 feet. So that's why this is 3. Okay, so your w of x is going to be equal to, or your slope here, it's going to be negative. And you rise over run, so you drop down 4 as you go over 3. Okay. And then we gotta find a starting point here, which I'm just gonna call this B for now. Alright. And so we'll find the starting point at that point, you're 1 foot down, and this is at 4 feet. Right, so 4 equals -4/3 times 1 plus b. So b is going to be 4 plus 4/3, which ends up being 16/3. Right, so w of x is -4/3 x plus 16/3. So that's how far we're starting out at. Right, so now write this out with force is your density, gravity, x, dA. dA is density, gravity, x, w of x, dx, which is going to be density, gravity, x, -4/3 x plus 16/3 dx. And then we can integrate here. Well, let me sap the integral. Haven't done that yet. So f is going to be integral of density, gravity, x, -4/3 x plus 16/3 dx. And it's going to go from 1 to 4, because we start 1 foot down, then we go 4 feet down. And so now when we integrate, we get density, gravity, actually before we integrate, let me do it right one more time. -4/3 x squared plus 16x over 3 dx. Now we can integrate. And so we get density, gravity, -4x cubed over 9 plus 16x squared over 6 from 1 to 4. Alright, so we don't have density, we don't have gravity for this. That's not what we're looking for. We are looking for expression here. So we will plug in the different values, but we're going to keep everything in terms of density, gravity. So we'll have density, gravity. When we plug in 4 cubed is 64. So -4 times 64 over 9 plus 16 times 16, so 16 squared over 6. And then plugging in 1, we'll have -4 ninths plus 16 over 6. And that's going to be, I'll try to simplify this out some. I'm not sure how much simplifying I can do though. Let's do it this way. 4 times 64 is 256. So -256 over 9 plus the 256 over 6 plus 4 ninths minus 16 over 6. Right, so we'll have density, gravity, negative 252 over 9. Which is 28. Plus 240 over 6. Which is 40. Okay, so I get 12 density times gravity. Okay. We don't know what density and gravity. I mean, we know what gravity is. We don't know what the density is. We didn't give that. So that would depend on whatever liquid this is in. Now, suppose the same plate is floating 1 foot above the water. So this is 1 foot down here where the water is. What's going to change is your width function. Okay, instead of it going from 4 down to 0, it's going from this point down to 0. And so the B value is going to change. We still have 4 here, but it's outside of the water. So our slope is still, we're still going from 4 here to 0, but we're crossing at a different axis point. So yeah, slope is still -4/3, but this point here is a different point. And so we can say, since we're 1 below, we can say that at -1 we're at 4. Right, so here we'll have 4 equals -4/3 times -1 plus b. So 4 equals +4/3 plus b. So we're subtracting this. So 4 minus 4/3 is your b, which has 12/3 minus 4/3 is 8/3 is b. So your integral is going to look very much the same. Integral from your density, your gravity, your x times your delta area, which is going to be -4/3 x plus 8/3 dx. And we're going to integrate this. Now we're going from we're going 2 feet down. So we're going to do this from hold on. I did this from 1 to 4. Yeah. So 4 feet down, 1 feet down to 4 feet down. Now I'm doing this from 1 to 3. And so I'll have density, gravity, times integral from 1 to 3 of -4/3 x squared plus 8/3 x dx. So density, gravity, -4x cubed over 9 plus ax squared over 6 from 1 to 3. So density, gravity, 3 cubed is 27, divided by 9 is 3. Right? You get 9, yeah, 3, okay. Plus 8 times 9 over 6 minus -4/9 plus 8 over 6. The density times gravity, we get a -12. That's going to be 72 over 6 is 9, plus 9, plus 4/9 minus 8/6. Alright, so I'm going to have to find a common denominator with these. -3 plus, I'll put this as 1 and then I'll put both fraction. So if I multiply by 6 and 9, well, 18, I'll do 2. So this will be 8/18 minus 24/18. And so if I'm multiplying to 18, this would be 54 over 18. So I get density, gravity. Alright, so -78, -70. That's supposed to be negative. We'll make sure I did my math right. Yeah, that's supposed to be negative. So let's see, cubed. And 3, you get 9. Just double checking my math. So -9, which is with 18 as the denominator, is for -54, -24, which is -78 plus 8 is -70. Okay, over 18. So density times gravity. Now reduce that down, 35 over 9, so -35 over 9. Okay. The last thing we're going to look at is moment and center of mass. Center of mass is the point on an object where the mass is equal to the space around it, or equally spaced on it. Moments for each particle of mass. The moment is m times x, so its mass times its distance away, where m is the mass of the particle and x is the distance along. So for every particle, let n be the total mass of n particles. So m, capital M, is m1 plus m2 plus all the way up to mn, summation of your mi's. And then the moment of the system about the y-axis will be if you're taking m1 times its distance along the x-axis, plus m2 times x2 plus m3 times x3 and so on. Where about the x-axis, it's m1 times y1 plus m2 times y2 and so on. And so we can think of this as summation I going from 1 to n of mi xi, and this is summation of I going from 1 to n of mi yi. Okay. And then we look at the averages. X bar is my over m, y bar is mx over m. Okay, so these are points where you're looking at average point there. Okay, so we're going to look at this with a uniform density for wherever the object is, and it's going to be bounded below by the x-axis and above by some function. Right, so for the moment of the system about the y-axis, we're taking x and multiplying by the function and integrating it from a to b times that density. And for the moment about the x-axis, It's a little different. 1/2 f of x squared dx integrated from a to b times your density. And then total moment of the system is just your density times your integral from a to b of f of x dx. And the way we find this x bar and y bar is we're going to take my over m, which works out to be the integral from of x f of x dx from a to b over just the area of a, the area a of it. This is, just so we're clear about this, this was density integral from a to b of f of x dx. That ends up canceling out in a sense, or we are just dividing it out. Alright, so let's do this. It'd be easier to kind of go through the process, and then you'll see how you're supposed to do it. So find the center of mass by a curve of y equals 2x bounded by y equals 0 and x equals 1. So 2, 1, 1, 2. So x equals 1, y equals 1, x equals 2, y equals 4. Actually, here, did that wrong. X equals 1, y equals 2. And then it goes down to 0 here. And then this boundary here, and your x-axis here. So we're looking at this area here. And we're finding the x bar, y bar, or the center of mass of this. Alright, and so it's going to be, for x bar, the integral from 0 to 1 of x f of x dx and then this is going to be over the integral 0 to 1 of just f of x dx. Right, I'll do the integral here in a little bit here. The y bar integral of 1/2 2x squared dx over the integral of 2x dx. And for this one, we're going from 0 to 2. And these limits and your x limits. Right, f of x is 2x. So we'll have, for the top one, 0 to 1 of x times 2x dx over 0 to 1 of 2x dx. And here we'll have 0 to 2 of, we'll get 4 over 2, so that'll be 2x squared dx over 2x dx. Okay. When we do these integrals, you know what, this also ends up being 2x squared. I'm just going to rewrite that, so I don't want to rewrite it again. When we do these integrals, we'll have 2/3 x cubed from 0 to 1 over x squared from 0 to 1, which that's going to be 2/3 minus 0 over 1 minus 0, which is going to be 2/3 over 1, which is just 2/3. So we're looking at 2/3 on the x, so about maybe here. And then y, we're looking at 2x to the third over 3 from 0 to 2, and x squared from 0 to 2. So with 2 you get 8, so 16/3 minus 0 over 4 minus 0. Which 16 divided by 4 is 4, so you get 4/3, which is about 1.33 or 1.33 repeating, if I get like that. So we're looking at about maybe right here, and so that point would be where your center of mass is. Okay. So let's look at one with sine of x. Okay, so here what we're going with is from 0 to pi. I'm going to draw this out. So like this. Right, so this would be 1. And what I want to do here is this happens at pi over 2. So what we're going to do is for my, oops, be going from 0 to pi over 2. Saving. Come on. Oh man, this is taking forever to save. There we go. Pi over 2. And this will be x sine of x dx. And then our mx is going to be from 0 to pi of 1/2. Did I have that right? Hold on. Yeah, my then mx. Okay. 1/2 sine squared of x dx. This goes from 0 to pi. And then m is going to be integral from 0 to pi of sine of x dx. Alright, so x bar is mx, or my over m. So integral from 0 to pi over 2 of x sine of x dx over integral from 0 to pi 1/2 sine squared of x dx. And y bar is integral from 0 to pi of 1/2 sine squared x dx over the integral from 0 to pi of sine x dx. Alright, so with these, since this is the last one, to kind of speed things up, I'm going to do each of these in Desmos, and then we can just divide them. Again, this is mx over m. Alright, so let's do that. Okay, so first one, all be integrals. From 0 to pi over 2. Gotta get down x, the sine of x dx. And then I'm going to copy this just so I can change it. 0 to pi of x dx. So that is your m. I wrote the wrong one in the first one. Okay. I'll change that here when I get back. And then this one will be 1/2 0 to pi sine of x squared dx. Alright, so with these, m is going to be 2, mx is going to be 0.79, and my is 1. Okay, so x bar, I wrote the wrong one here, I meant to write m. So that, not that it's going to matter, I'm going to use this mainly anyways. Sine of x dx. So x bar my over m. So 1 over 2. The other one will be 0.79 over 2. Why? I don't know why it has to take so long to save. Okay. And then why it saves so often. So 1 over 2, and then x bar is 0.79 over 2. Which is about 0.395. Alright. In the next video, we'll be on sequences, and it's a pretty long chapter, but it's a pretty important chapter. I'll see you then. Bye.